Hi everyone and welcome back. In this video, we're going to talk about the system design of the proximity service. Proximity service works directly with world map or maps, and what it does is it helps you to find the closest objects to where you are located. For instance, if you think about the Google Maps and you look for the closest restaurants or coffee shops, or it can be a Yelp and that looks for the closest businesses or facilities that you look for in your area. So all of these services use proximity service behind the scene. In this video, we're going to talk about the system design of Yelp as well as drill down into how we can represent the world map as a data structure so it allows us to find the n closest places. So high level, we want to implement a functionality that based on our own coordinates where we are located finds the n places in the radius around us. So in this way, we need to work with maps. And high level, when we think about maps, first that comes to mind is that we might use graph and just have all the objects, all the businesses or coffee shops on the map connected as a graph where the objects would be vertices and the edges would represent the distance between different objects. But doing it this way would create an incredibly large graph of objects and edges that would be really hard to traverse. Also, a lot of places on the earth are overpopulated, like big cities like New York and San Francisco, for instance, where you have a lot of different objects on the very limited area. So the brute force approach would be just to use a Postgres database, for instance, and store all the places with their coordinates in the database. And when we want to search for the objects, we would just use a database query where we would just find a range of objects between our coordinates and the radius around us. But this approach is obviously not very efficient because we would need to scan all the places around the world, which is a very big database. So one of the improvements we can make is to split the world into grids. So we have multiple grids and different number of places on those grids. So our Postgres query would be limited to a specific grid instead of running across the world map. So this way we reduce the size of the query, but still it would be very inefficient because we would need to scan through a lot of rows every single time we want to find those objects. But the idea of splitting the world into multiple grids is fundamental here, and the algorithms that we're going to discuss will be built on top of this. There are multiple ways the map can be represented as a data structure for easier processing, but fundamentally there are two approaches. The first one is a geohash, which is based on splitting the map into different grids and then have them stored in a key value database so you can easily search the specific grid that you're interested in. And the second one is R tree based, which is tree based, and there are different variations of this implementation based on the number of children that the tree has. You can think about the quad tree, for instance. This is the easiest representation of the R tree map, just because it very closely overlaps with the geohash and is just easier to understand. The first algorithm we're going to look at is geohash, and this is where you take the world map and you split it into multiple grids. As you can see on this diagram, there is a single grid that consists of 6 blocks vertically and 8 blocks horizontally. And as we go deeper, you can see that every single grid inside that grid is split with additional number. So the grid 9 is split into 32 grids, which are 9P, 9N, 9G, etc. So every second level grid has 2 characters in it. And then as you go deeper, you get 3 character and keep going until you have, for instance, 5 characters and they cover a very small area. And then if you go deeper, you will get all the way to 8 characters that represent a very small area that perhaps covers a specific place. In our case, it's a Starbucks. So high level, the less characters in the key of the grid, the bigger the area is. So for instance, if we sit at this Starbucks and we want to find the closest restaurants or coffee shops to where we are located, all we need to do is just remove one character from the end. And by doing so, we'll get all the upper level grids that surround our own grid. Now, as we have this high level understanding, how are we going to store it? And the easiest way here to store would be just to use a key value database like Redis and store this data where key would be a number of characters, which is the name of the grid, and the value would be a list of objects that exist in this specific grid. Let's zoom out for a second and look at this picture here. As you can see, number 9 block covers almost the whole United States, which means it'll have a lot of blocks or objects inside of it, versus block 8 is in the middle of the ocean and doesn't have any places. The way we're going to keep breaking down our grids into more grids would be based on the number of places that exist in that grid, which means that if it's a grid number 8 and it doesn't have, let's say, more than 500 places in the middle of the ocean, then we wouldn't break it lower than, let's say, 2 characters deep. But in case of the grid 9 that covers almost all the United States, we would keep breaking down our grid until every single grid has at most 500 places, for instance. This way, we have that granularity that allows us to do a very targeted queries, especially if it's, let's say, San Francisco. Maybe then we would just have even more grids where we would cover a areas of less than kilometers and find all the places within the 1 kilometer radius. So having those granular grids inside the big grid would allow us to do that. And as I said, the search here would be very simple because first, as we know our own coordinates, we find the grid where we are located. And then we have a key of that grid, which is a list of characters, let's say 8 characters long. And then if we want to find objects, let's say in the radius of few miles, what we do, we just remove the last character of that string and then use it that as a prefix to find all the blocks one level higher. As you can see in the diagram, it would look like this. As we identified our own location, we have access to the grid where we located and all the places around us located. But if there are not enough places, all we do, we just increase the search area by removing the characters from the end and increase it until we get the right number of places that we need to show to our customer. The next approach we're going to talk to is how to represent a map using R-tree. And specifically, we'll talk about the Quadtree implementation. Quadtree, as you can see on this diagram, means that every single parent will have 4 children. Similar way, we would take those blocks, high-level blocks, and keep breaking them down into 4 pieces until we get so granular, so every single piece will not have more than 500 places in it. It means that high-level block on the ocean will likely not have that many children, but the block that covers the United States, for instance, will have a lot of children and they'll be broken down further and further until every single leaf node has no more than, let's say, 500 places. As you can see here, this is how the levels would look like. We would have a tree that is broken down unevenly, so it wouldn't be a balanced tree, it would be unbalanced tree, and all the leaf nodes would have the list of places that belong to those smallest grids. Top level node has 200 million places, and then we keep breaking down that node into 4 children further and further until we reach and go all the way to the bottom where every single leaf node has less than 500 places in the grid. This same data structure, Quadtree, can also be represented as a geohash by just breaking down grids into 4 different subgrids instead of 32 subgrids as we looked at previously. You can see NV, NE, SV. This would be a geohash string representations of the grids if we were to represent this tree as a geohash. So these are just different data structures on how we can represent those grids and query them. It's important to mention that every single node is represented as a small grid that is surrounded by the coordinates. So if we want to look for our own location in this tree, for instance, we would take our own coordinates, latitude and longitude, and then use them to know what children we need to go to. So we will start all the way from the root and then keep going down based on the coordinates until we add to the very bottom to the leaf node. And once we at the leaf node where we are located, similar way, we get all the places that belong to this leaf node grid. And then if we want to increase the search area, there are multiple ways to do it. The first way is just to have a links back to the from children to parents, so we can go all the way, so we can go upper 1 level and then find all the children, which would be a surrounding area around us. And the second way would also be if we want to query the neighbor nodes, we will have to have a double linked list that would go through the leaf nodes. This way, once we found our own leaf node, we can use the double linked list to go left or right through their leaf nodes and find the neighbors or find enough places around us to return to the customer. Now, as we reviewed how to represent the world map into either the tree or a key value data store, let's look at how we would implement Yelp or Google Maps closest location. High level design would be like this. We need to cover two main functionality. The first one is adding new places to a database. So as the businesses or places created, we need to make sure we store them and update our data structures so they are searchable by the customers. And the second endpoint would be for users pretty much given their location, find the nearest objects that they look for around them. The business information would consist of different metadata as well as probably different pictures. So we would have a business service that would be receiving and storing that data. We would have a place ID, and the data would be partitioned by the place ID. Partitioning by the place ID would give us a consistent and even data distribution across multiple servers, as well as the overall we would have a primary service for writes, because writes wouldn't be that frequent as reads. So we'd want to optimize the database for reads, and to do that we would add multiple replicas either in the same site or across multiple regions. So the data would be written to the primary and then replicated across multiple regions. And for the location-based services, we would have a service which is an aggregator service that would send the request to one of our data structures, either the GeoHash or Quadtree, and then retrieve back a list of places based on the specific radius. What we didn't talk about is sharding, and specifically sharding of our location-based database. So it would be either the GeoHash or Quadtree. What we would store in our Redis instance would be a lot of keys that represent a specific block, and the value would be a list or likely a set of the place IDs. This way, when we add a new place to our database, first, we use the coordinates to find the right grid in our GeoHash, and then we just insert it into the set of places. This way, we have a very quick write to the Redis GeoHash, as well as we remove the duplicates by maintaining a set of place IDs in the value of the GeoHash. If we have a Quadtree, we would need to find a way to shard it too, as well as maintain a master replica deployment. So we would have a Quadtree that would be responsible for writes. So every single time a new business is added, we would write that new business into the master Quadtree, update the tree, and then the data would be replicated across the replicas. So when we search for places inside the tree, we would only search on replicas and not on the master. If we were to shard our Quadtree, we would need to use a place ID as a sharding key. And this is it for this video. I hope you found it useful. If you liked it, make sure you like and subscribe. If you have any questions, make sure you comment under the video, and I'll see you in the next one. Bye.